Hello everyone, this is Dr. Zach. For today's lesson, we are going to be reminded of numerical integration techniques, and also I'm going to introduce a new one called Simpson's method. So the lesson preview is a reminder of Riemann sums and trapezoidal rules and how they are used to solve your integration problems. Go ahead, turn the video off, and complete the lesson preview. Afterwards, review your work. For question A, you were reminded that you're going to use right-hand endpoints. First, you need to find your delta x. Now, fortunately, for each one of these problems, your delta x is the same amount. So we can use the old b minus a divided by n in order to find that delta x. We're going to multiply delta x times the height of f of x for each one of these values. So that's why we're going to take the height of each rectangle that's built with our right side. So reminder that the right side of the triangle is going to be created at 1/2, created at 1, then we'll have one at 1.5, and one of the rectangles will be at 2. Add them all up and we get a 13.25. Notice the notation and the parentheses. Those are important as you create each problem. For the second question, you're asked to find the area under the curve between 0 and 2 using trapezoids. So this time when we use our trapezoids, the formula that we want to use is 1/2. We'll have the height. Your height is part of delta x. Then we're going to multiply by base 1 plus base 2. Since all of the delta x's are the same again, we're going to use this nice little shortcut, which is 1 times the first term plus 2 times the second term. That pattern continues until we get to the end, and then it's going to be 1 times f at 2. And notice the answers are very similar for questions A and B. Now question C, we're starting to do something a little bit different. This one says approximate the volume, where we're revolving about the x-axis. So if we're revolving about the x-axis and using x values, we're going to follow the volume formula pattern pi r squared. So we're going to take the radius of the x-axis, which happens to be f of x, and we're going to substitute that into our trapezoidal rule. So again, we will have 1/2 times your delta x. This time we have pi involved because the formula has pi r squared. So that's where this pi comes from. Now the radius is being squared. So we're going to take the height of each one of these and square them. So that's a little different than what you've practiced in previous problems. So make certain that you understand what's happening here. And the last term is also squared. Add them all up. You have 79.7533 pi. Now for question D, again, we're going to approximate the volume using midpoints. Midpoints makes this a bit more interesting. But this time we're revolving about the y-axis. So we're going to spin y, use x. The formula is 2 pi r h. When we spin y, use x. So we first must write the integral. So we have 2 pi. Here's my radius with respect to x. And then the height is f of x. dx makes it a volume problem. Put it all together. Midpoints, we're going to have 2 pi. Here's your delta x. Now, notice the pattern that we're following. The formula is x f of x. So using midpoints, here's my x value. Here's f of x. Here's the x. Here's f of x. And we continue that all the way through. I need x, f of x, x, f of x, because that's what is the function in your integral. It's not plain old f of x. And then we come up with your estimate is 28.635 pi. So these are great ways for us to use numerical integration in order to estimate integrals. If you need reminders about your Riemann sums using rectangles, I've listed all the information. I've also listed the information for your trapezoidal rules. Just keep in mind that delta x's do not have to be the same. They could be different, in which case you can't use these nice patterns in order to write your approximations. So we know that the trapezoids will give a better approximation for area than our rectangles. And the reason for that is that we have less value that's going to be overestimates or underestimates when we build these trapezoids. But we're still using these straight lines, which doesn't give us the best value. So I'm going to introduce a new method, and that one's going to be called Simpson's method. So instead of trying to use corners in order to create these estimates, what if we were to use curves? Wouldn't our curves give us a slightly better answer if we had multiple curves throughout as we were building these estimates? Now, what I'd like you to see is that I am building lots of parabolas where these corners are intersecting our function. Now, lots of parabolas are going to have less error than if we were to use the corners of our rectangles or the corners of our trapezoid, because we're always trying to find a better estimate when we cannot determine an exact value. And that brings us to Simpson's method. Simpson's method is going to be a way for us to find numerical integrations based upon parabolas. Now, you know that the general form of a parabola is ax squared plus bx plus c. So if we were to integrate that parabolic curve, we will come up with this lovely value right here. So I'd like you to spend 10 minutes, no more than 10 minutes, trying to prove that the integral of your parabola is equal to the expression that we have here. So spend 10 minutes, no more than 10 minutes, on that little proof. So I'm not going to solve this problem for you because I really wanted you to give it a good try. I will throw out some hints. Integration is where we should start. Don't forget to evaluate your endpoints, group strategically, and then factor. Now that you've worked on the proof for the integral of a parabolic curve, what I'd like to do is use parabolic curves in order to find the area under a curve. In this particular example, we want to go from x equals 0 to x equals 4. We're going to take this area and divide it into n partitions. In this particular example, I'm going to use 8 partitions. Now, when we have 8 partitions, or n partitions, we're going to split the area into n divided by 2 integrals. So that means that we're going to be writing 4 integral problems, and each one of those integral problems is going to be include the antiderivative of a parabolic function. For each integral, we're going to use a left endpoint, a midpoint, and a right endpoint to find the quadratic equation. So if this was our curve and we're looking at our midpoints left and right, we would draw the parabolic curve related to that problem. Now, if we draw our second integral, we will have a left, a midpoint, and a right. So this parabolic curve is kind of heading upwards. Then we're going to do it again for our third one. We will have a left, midpoint, and right. This parabolic curve again is going upward. Notice it doesn't necessarily mean that the vertex is in the middle. And for our last one, we're going to have a left, midpoint, and a right. And again, we will draw a parabolic curve. So what I'm hoping that you see is that these 3 estimates are going to give us a really good area estimation for our problem. Better than the rectangles, better than the trapezoids, because we've gotten rid of some of the error. All right, now, with that being said, what do we need? We need 4 different integrals. So we are going to be integrating from 0 to 1 of our first parabola. So I'm just going to call that parabola 1 of x dx. Then we're going to find the next one, which goes from 1 to 2 of our second parabolic curve, and with the area of that, so that of course is integration. And then we want to go from 2 to 3 for our third parabolic curve, so that'll be p3 of x dx. And then we want the fourth parabolic curve, which is going to go from 3 to 4 of p of x dx. Sorry, p4 x dx. Now, if we could integrate each one of these, then we're going to be able to find the estimated area under the curve. Well, we already worked on that. That's what your entire practice problem was about when you were trying to solve for this formula. This formula uses the endpoints. Your b minus a is divided by 6, where you substitute in your endpoints, and then you're going to be set. So let's see what happens. Starting with the first parabola, we're going to have our b minus a, so b is 1. We'll have 1 minus 0 divided by 6, and then that's going to be multiplied by, so we're substituting in the a values, so that'll be p at 0, plus 4. Now, a plus b divided by 2 is the midpoint, so that's p at 0.5, plus, and then we're going to have p at 0, p at 1. All right, now that's our first parabola, and we need to do this 4 times. So if we do this 4 times, we're going to add those together. Next, we're going to have 2 minus 1 over 6. Wait, that's 1 again. Then we will have p at 1 plus 4. Now I need the midpoint, p at 1.5. Then we'll have plus p at 2. So we're going to see some lovely patterns happening here. Work on our third one. So that's going to be 3 minus 2 over 6. And then we'll have p at 2 plus the midpoint, which is going to be 4, p at 2.5 plus, and then we have p at 3. Next, we're going to throw in our fourth parabolic curve, and that one will be 4 minus 3 over 6, p at 3 plus the midpoint, which is 4, p at, and then we're going to have a 3.5, and then lastly we have plus p at 4. All right, now take a look at this beautiful math and what's happening here. If you look closely, you should find some lovely patterns. We're starting at p at 0. We have 4 with the next step, and then we've got 2 p at 1s that we're going to be adding together. 4 with the next step, 2 p at 2s. So we have lovely patterns that are happening that were very similar to the patterns that happened when you were building the trapezoidal rule. Something I'd also like you to notice is if we think about our delta x. So delta x in this particular problem was 4 minus 0 divided by 8, which gave us 1/2. So where we had b minus a over the number of partitions. So as we look at this value 1/6 that's in front of each one of these little parabolic evaluations, what you should notice, or hope that you notice, is it's actually 1/2 times 1/3 is going to be equal to the 1/6. So you have delta x multiplied by 1/3. Now, I want you to think for a minute. When you are integrating a parabolic curve, you add 1 to your exponent, which gives you x to the 3rd, and you would divide it by 3. So that 1/3 is not coming out of thin air. That is coming from your integration rules. So after exploring that one problem, let's take a look at what's happening with our formula. We have an antiderivative from a to b of f of x can be approximated by, now notice this says b minus a over 3 times n. I'd rather you remember it as b minus a over n times 1/3, so that you're getting the idea that it's your delta x times 1/3, just like when you work with your trapezoidal rule, it's your delta x times 1/2. So delta x times 1/3. Then you have this lovely pattern that's happening. For each of your partitions, it's going to be f at 0. The next value is going to be 4 times f at the next value, plus 2 times f at your third value, plus 4 times f at the fourth value. So you have this alternating series going 4, 2, 4, 2, 4, 2. It ends at 4, and then of course you have your last value. So very similar to your trapezoidal rule, but this one gives you a better answer because you're using curves instead of those straight lines in order to estimate the area under a curve. Let's take a look at example 1. As you take a look at the integral, use substitution will not work in order to complete this integration. You do not have a method to find the exact integral value. So what we'll do is use Simpson's method. For this problem, we're told to use 6 partitions. So n is equal to 6. That makes us understand that delta x, which is your b minus a, divided by the number of partitions, which is 6, is going to be equal to 1/3. So I'm going to declare f of x to be the expression inside the integrand. We have square root of x over root x plus 1. So Simpson's rule says that we're going to take 1/3, which is your delta x, and multiply it by the factor of 1/3. Then we're going to take our first endpoint, which will be f at 0, and add it to 4 times 1 increment. So that would be 4 times f at 1/3. Plus, following your pattern, next we'll have 2 times f at 2/3. Plus, we'll have 4 times f at 1, plus 2 times f at 1 and 1/3. Then we will add 4 times f at 1 and 2/3. That leads us to our endpoint, so we're just going to add in f at 2. And we're going to substitute all of these values into the function that I've declared f of x. And once you do that, you will have your final solution. Now, double check, but your approximation should be 0.5858 once you've completed all of the addition. I'd like to point out right here that the n value has to be an even number. If your n value is not even, then Simpson's method cannot be used. So keep that in mind as you look through your problem set. For example 2, we are looking at a tree trunk that is 160 feet long. At a distance x feet from one end, its sectional area is given to us in square feet by the following table of intervals. These intervals are set at 20 feet. Use Simpson's rule to approximate the volume of this tree trunk using n equals 8. So we need to find the volume. And since we've been practicing volume using cross-sectional area, we know that the volume is going to be equal to the integral from a to b of our area with respect to x dx. Given that, we know that the volume is going to be equal to the integral, in this case, from 0 to 160 of the area that's given to us in our table, a of x, multiplied by dx. So that's what we're going to estimate using Simpson's method. So we're going to find first our delta x. Delta x is our b minus a, so the 160 minus 0 divided by the number of intervals, which is 8, which gives us delta x is 20, which works out very nicely, doesn't it? So we take 20, which is your delta x, we multiply it by the factor of 1/3, then we're ready to do our substitution. So we start with the area at 0. We move by delta x, but we want 4 times the next value, which will be the area at 20, plus 2 times the area at 40, plus we're going to add 4 times the area at 60. Next, we're going to add 2 times the area at 80, and we're going to continue this pattern until we get to 160 as the final end point. We're almost there. Another 2, area 120, plus 4 times the area at 140. Now we're at the right-hand endpoint, so that's just going to be the area at 160. Next, we're going to read the table of values. We have 20 over 3 multiplied by our area at 20, which is 120, plus 4 times the area, that was area at 0, 4 times the area at 20, which is 124. And you're going to continue to substitute these values in to your expression. Afterwards, simplify and add up all of your terms. Once you do that, your final answer should be 21,960. Now let's think about the units. Area was given to us in terms of feet squared, and dx is also feet, so this will end up as a feet cubed. Double check your substitution and verify the answer. For our third example, we are given a table of values where F is the force in pounds acting on the body in the direction of motion, and S is displacement in feet. We're going to use Simpson's rule to estimate the total work done by the force. Work is defined as the integral from A to B of the force as it's pushed along in the direction of motion. So with that, we're going to be able to integrate. We're told that we have 10 partitions this time. So the delta x, or in this case, delta s, is going to be b minus a divided by 10. So what are our b and our a values? Our b value is going to be 50. The a value is going to be 0 over 10. So our delta s is 5. So if we're going to solve the integral from 0 to 50 of f ds using Simpson's rule, we know that it's delta s, which is 5, multiplied by the integrating factor of 1/3. Then we will have the first value, so that's going to be f at 0, added to 4 times f at 5, plus 2 times f at 10, plus 4 times f at 15. Then we'll have plus 2 f at 20, plus 4 f at 25, and continue with the pattern until we get to our endpoint of 50. Remember, your last term doesn't have a multiplier. It's just going to be f at 50. All right, use your table to fill in these values and simplify. And once we do that, so f at 0 is 100, then we will have 4 times 80, 2 times 66 gets added in, 4 times 56, and you should see this lovely pattern. Finish it up with the 28, multiply, add, let's see what we get. 2,490. Please confirm the answer. Now, what you should also be asking is, what are we measuring in? So pounds is what your F is being measured in. Distance, your DS, is being measured in feet. So this is actually foot pounds, and that is how you measure work in the British system. All right, so what we have learned today is that Simpson's rule is another method to use to solve integration problems numerically.